Okay, so yesterday we did long division, yes? Okay, we'll do a couple more of those today, but we're going to first show how synthetic division is a shortcut to that, okay? Yesterday, towards the end, we discussed how long division is, it's like a lot of things in mathematics where it's like it's the go-to thing that will always work, okay? So meaning that if I want to divide a polynomial of any degree by another polynomial of any degree, long division is the tool that will work. So if I have like a fifth degree polynomial and I want to divide it by a third degree polynomial, long division is my go-to thing, okay? Now, if I want to take any polynomial of any degree and divide it by something that is linear, then synthetic division will work in that situation. Does that make sense? So my hope is that I get you to understand where synthetic division works. It only works when the divisor is something like x minus c, okay? Meaning my divisor can be like x minus 3, it can be x plus 2, something like that, right? I cannot use synthetic division when I want to divide by like x squared plus 5x minus 3. There is no way to do synthetic division that way. Does that make sense? So what we would do is we would do long division for that. Okay. Now you can probably piece some things together to help maybe use synthetic division in lieu of long division, but it's messier. Yes. Right. So if it was like 2x plus 4, then that's linear, and basically what we would divide by here is this thing equal to 0, so we'd solve that for equal to 0. And we'll see some examples of that in the future. But as long as it's linear, because everything that is of this form can eventually, with fractions, all that kind of stuff, be written this way. Okay, good question. So let's talk about doing this process with a problem that we did yesterday. So we did this problem, 2x cubed minus 7x squared plus 5 divided by x minus 3. We did that yesterday in class, okay, with long division, okay? And whether you have it in your notes or not, I've got it up here still, okay? What I want to do, though, is compare the time that it took to do both of these, compare the amount of work and the organizational work, but also at the same time compare the amount of information, because this is very informative. There's a lot of stuff here that is very detailed work. When we do synthetic division, we lose some of that detail, okay? But we gain efficiency and speed, okay? So what we're going to do with long division, you guys have done some of this, or synthetic division, you've done some of this in the past. So everybody in the last class, like once we started writing this stuff down, it jogged their memory and they recall doing this. So first thing you're going to do is you're going to take the coefficients of the dividend. Okay, so I'm going to take 2. I'm going to take negative 7. Okay, now this is one where you have to have the placeholder. Yesterday I said that with long division, you can maybe get by without placeholders if you're paying attention to detail. Okay, with synthetic division, you absolutely will fail every single time if you do not put your placeholders in. Okay, and then I'm going to put my 5 in. So if I have x to the third as my leading degree, I better have 4 positions in my my coefficient row here. Okay, and because because that's a constant with an x raised to the 0, essentially, whatever that number is, add 1 to it, and that's how many items you should have listed in your rows. Does that make sense? That might help you remember whether, before you start going through this entire process, whether you've incorporated your placeholders or not correctly. Okay. Then you're going to put a box out here. And what goes in that box is that C term. And remember, we define this by x minus c. So basically what we do is we set that equal to 0 and solve for x. So it would be x is equal to c. So c goes out there. So if I have x minus 3 is equal to 0, x equaling 3 will go out there. Does that make sense? And that's where we get to Anthony's question about, what if the x had a coefficient in front of it? Well, we would go ahead and solve that equation. If it was like 2x minus 3, we'd solve that. We'd put a 3/2 out there. Okay, so everybody okay with that? You guys remember seeing maybe a little setup like that last year? All right. Now, the way I do it is I always draw this line here. Okay. It just separates my work from basically my quotient here in a moment. And as you go through different textbooks, you're going to see different structures for synthetic division on how they organize, where they put the line and that kind of stuff. I've seen it written this way where they don't put a box there, but they put like a box around these, and then they don't put the line there. It's just weird structure. And it's just per author. Okay, this is the one I learned when I was in school, so it's the one I use. But what we're going to do is the first thing we're going to do is we're going to bring down this 2. Okay, that's all you. You always bring down that first term. And that 2 right there is analogous or corresponds to that 2 that we found yesterday doing long division. Is that okay? Okay. So now the next thing we do is we multiply this 3 by that 2. And what's 3 times 2? 6. And then that 6 gets placed underneath your next term. Okay? So I'm going to go back up to the long division. Didn't we take this 2 times that 3, and it became that 6 right there? Okay. And that 6 got placed underneath the -7, right? Is that 6 placed under -7 here? Okay, so we're going to add straight down, make it -1. Okay, now we take that 3 and multiply by -1. That's going to give me -3, correct? And the same thing, take that -3 times this -1, ends up, it's actually this -1, but it ends up giving me that right there, correct? The 0 and the -3 are stacked on top of one another. Add straight down. And now I do the same thing with the 3 and -3. I multiply those together, and then that product goes there. I'm going to add straight down, and I get -4. And that 5 and -9 and -4 is that right there that we did in the long division. Okay? So my hope is that you see here that it's really doing the same thing, correct? Okay, now would you agree that the synthetic division is a lot cleaner looking? Okay, but would you agree, and it was a lot more efficient, but would you also agree that we've lost a lot of information here? Yeah, there's no x's anymore, right? Okay, so obviously this is my quotient here. Okay, what I like to always do is I like to, on my last term, prior to my last term, in my quotient row, I put that little line there. What's that line remind me that -4 is? It's my remainder, okay? But now, this is where we've got to understand a little bit about division. When I divide, if I take x to the 5th, and I divide it by x, what is that result going to be? X to the 4th. If I take x to the 8th and divide it by x, what's that going to give me? X to the 7th. So what we're saying is if I take x to the n and I divide it by x, that's going to give me x to the n minus 1, right? That's what's going on here. We took x cubed right there, and we divided, this was x to the 1st, correct? When I divide them, what is this quotient's x going to be? X squared, okay? And that there is, the context that I was talking about us losing when we do synthetic division, okay? You always got to remember what was the leading degree of my dividend. I'm always dividing by a linear term, so I need to know that it depreciates my quotient row by 1 power, 1 degree. And then you will have all the x values here will be, or x terms will have a descending order of exponents. And you're not going to miss any. You're not going to skip any. So if it's x squared, this is going to be x to the first, and the next one will be x to the 0. If this was x to the 7th, you would have a value for x to the 6th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, x to the 0, right? You would not skip any. Does that make sense? Yes. Right. So this was x squared. This was x to the first, right? Does that make sense? Is that what you're asking? If you got 0 on the bottom, so let's write this one down, and then I'll give you an example in a minute. So the quotient row here would be 2x squared minus x minus 3. Okay, that's q of x. The remainder is -4. The divisor was x minus 3. And if you remember, the original polynomial p of x was equal to 2x cubed minus 7x squared plus 5. I like to write those 4 things down because then they might ask me, okay, write p of x over d of x is equal to q of x plus the remainder divided by the divisor. Well, if I've got those individual components, and that's pretty easy to say, 2x squared minus x minus 3 plus my remainder of -4 over x minus 4. And we see that is exactly the same thing that we came up with right there yesterday, correct? Okay. Or they may ask me to write it in the format that p of x is equal to the quotient times the divisor plus the remainder. And I can write that then as 2x squared minus x minus 3 times x minus 3, and then plus my remainder of -4. And that's exactly what we had yesterday as well. Yes? I don't know why I made -4. It should be -3. Did I do that yesterday too? It should be -3. Okay. I'm sorry. Say it's not okay. It is x minus 3. All right. Sorry. So what Jim was asking was, and this is going to be, I'm just throwing numbers out there, so I don't know if this is going to be legit. So let's say that we've got, and I'll just put like number. So let's say this was like x to the 4th. This would be 3rd, 2nd, 1st, 4, 3, 2, 1, and there's my constant. Okay, but let's say that when we're adding straight down, so I bring that number down. Let's say this number, when we add down, gives me 7. This one gives me 0. This one gives me 4, and that one gives me 5. So your question was, so if this was x to the 3rd, what would this one be? Is that what that's x to the 3rd? This is x. So this is x to the 4th. So that one's x to the 3rd. It's one less. So this one is going to be x squared. This would be x to the 1st, and this would be x to the 0. Does that make sense? And then when you're writing it, then Jim, and obviously you don't need to incorporate that one then when you start to rewrite it as the product down here. Does that make sense? Does that answer your question? Okay. But if you don't put these zeros in, like we did right there, think about this. You would have then put this -3 underneath a 5, and you're going to get the incorrect results. Okay, so we need to have placeholders when we're doing this. And like I said, no matter what this row becomes, if I started with x to the 5th, x to the 6th, x to the 7th, every term then will show up down here. So if this is x to the 7th, then down here, your first term will be x to the 6th, and then you will have an x to the 5th, an x to the 4th, an x to the 3rd, an x squared, an x to the 1st, and a constant. Okay, but now some of those coefficients might indeed end up being 0. It just depends on what they, how those numbers work out with one another. Is that something we can do? All right, so let's do one more here. We'll do it long division, practice long division, and then we'll practice synthetic division. So doing long division, again, we're going to go 3x cubed plus 9x squared minus 5x minus 1. Okay. We don't need any placeholders there. And we're going to divide by x plus 4. So there's two ways of thinking about how I need to find this first term. I can think in the direction of what do I need to multiply x by, so it becomes 3x cubed. Okay, so you can use multiplication to figure this out, or you can reverse it and say 3x cubed divided by x will give me 3x squared, and that is the answer to that question I first asked, right? 3x squared is what I need to multiply x by to get 3x cubed. So that's what goes in the first spot here in our long division. And then we distribute. So 3x cubed, then plus 12x squared. I like to add these straight down, so that means I got to make these negative and multiply everything by a negative. And then that's going to give me, when I add straight down, it'll give me negative 3x squared. I'm a fan of bringing down all this stuff that I haven't used. I like to bring that down next. And again, you guys can structure that how you feel comfortable with it. But now the question is, what do I multiply this negative 3x squared by? What do I multiply x by to get negative 3x squared? Negative 3x. So multiply that, gives me negative 3x squared minus then 12x. Multiply everything by a negative on that bottom one, and then add. Those go away. Gives me 7x minus 1. And now what do I multiply x by to get 7x? 7. Gives me 7x plus 28. Negate that row. Add straight down. Gives me negative 29. Okay. Now we stop. Kind of talk about why. Well, the algorithm says you stop once your remainder is of a less degree than your divisor. Okay. So what we do is we just say remainder here of negative 29. But we've also been discussing how, when we write this as the quotient 3x squared minus 3x plus 7 plus then the remainder over x plus 4, the divisor, isn't that thing divided by that thing? And isn't that showing me, it's implying that I'm dividing negative 29 by x plus 4? So it is showing or going through that process. Anyway, we are doing that division. It's just implied. It's not explicit. So that is one way. So remember, that is the quotient of x plus the remainder divided by the divisor. Okay. If we were doing this in synthetic division, okay, my hope is that when we do this, you guys can see the contrast in the speed that this occurs. We go 3, 9, negative 5, negative 1. What is going to go out in the box? Negative 4. Yes. Yes. So we bring our 3 down. Multiply gives me negative 12. Add straight down gives me negative 3. Multiply again gives me positive 12. Add straight down gives me 7. Multiply again. Negative 28. Add straight down gives me negative 29. That's your remainder, right? Now, what was this? What was that term right there? It was x to the third. So this one's going to be x squared, and then they are all there, depreciating by 1 each time. So it'll be 3x squared minus 3x plus 7. That's my quotient, plus then my remainder over my divisor of x plus 4. Or we can say P of x is equal to the quotient times the divisor plus your remainder. Those are all alternative options. I think you're going to need to eventually, based on where this is leading us, this is going to become your preference of writing it that way. I show the other one because every once in a while WebAssign will ask you that way. Okay. Someone in the last class asked, is there a special name for these two formats? Okay, and there's not. And I think you'll find out today in WebAssign that if they want you to do it in the one on the left there in that box, they will say in their instructions, write your answer this way, and they'll show that. Or they'll write it in the directions if they want it written this way. But again, like I said, this is going to be a preferred technique by you eventually. Is this something we can do? Okay, so we have some theorems here that in the future we might discuss if we have time. We got two theorems here. It's called the remainder theorem and the factor theorem, and they're going to be linked together in a moment to actually allow this synthetic division to be purposeful for us. Okay, because right now it's just us like doing this algorithm, and yeah, it's great, and we can get this result, we get this quotient, we can do the division, but what does it mean to us? Okay, what can we use it for? So the remainder theorem says if the polynomial P of x is divided by x minus c, the remainder is the value P of c. Think about what that means. That means if I take a function, this polynomial P of x, like up here, if we take 3x cubed plus 9x squared minus 5x minus 1, and we find the remainder of this, okay, that remainder, they're saying, is identical to evaluating this thing at -4. Okay, so let me show you that with Desmos real quick. All right, so we've got, why does that keep? All right, so we had 3x cubed was it plus you said minus 5x? Okay, so that's our function, right? We just did long division with x plus 4, right? Okay, so that means if we were to evaluate, we got -29 as the remainder. If we evaluate this thing at x equals -4, what do you recognize we get? We get the remainder -29. Okay, so the remainder is identical to the evaluation at any point. So if I want to divide this thing by like x plus 5, then I know the remainder is going to be -126. Does that make sense to everybody? Okay, so that's a key theorem. Okay, by itself, probably never going to use it a lot. Okay, we'll do an example here to demonstrate this, but by itself, we don't usually use the remainder theorem other than just to see that it's a unique maybe feature. Okay, so let's find the quotient remainder when P of x is divided by x plus 2. So let's do long division here, or synthetic division. Let's go 3. Do I need any placeholders? I need a placeholder for x squared, right? So we go 3, 5, -4, 0, 7, 3. What is going to be out in the box here? -2. Okay, so I can bring my 3 down, multiply, bring my -5 down, multiply. That's going to give me, what, 8 here? Oh, can't add, multiply. What am I doing? Come on, guys. Help me out here. Bring my 3 down, multiply. That gives me -6, right? I was multiplying. For some reason, I was taking the 2 and multiplying by the 5. I don't know what I was doing. So -2 times 3 is -6. Add that straight down, -1. Where are you at on that one, Jackson? You know, where you're a producer, then you got to be on top of things. All right. So -2 times -1 is 2. Gives me -2. So it's going to give me 4. -8. Multiply gives me 2. And now I get 5, right? Okay. So if we take this function, I think I already have it typed in. If it lets me go back far enough. Nope. If we take 3x to the 5th plus 5x to the 4th minus 4x cubed plus 7x plus 3, and we ask to evaluate it at x equals -2, right? Plug that in. Does it give me the remainder of 5? Yeah, okay. So what I'm doing here, think about, obviously, using the technology to circumvent some handwritten work, right? But do you guys remember back when we did work with functions, that a lot of times we would ask you to evaluate functions, right? Okay. And think about before calculators, before Desmos, before TI-83s, A4s. Maybe when your parents and people of that age were in school and they wanted to evaluate things in a quicker way, instead of taking and saying, okay, I'm going to plug -2 in for x. I'm going to raise it to the 5th power. What does that give me? Multiply it by 3. Now plug in -2 to the 4th power. What does that give me? Multiply by 5. Now put -2 in and raise it to the 3rd power. Multiply by -4. And then adding all those together, instead of doing that, they would have used the remainder theorem. They would have done this synthetic division. They would have gotten 5 and automatically known, if I would substitute -2 in for that polynomial, everywhere I see an x, and evaluate, I'm still going to get 5 as well. Does that make sense? So it was a shortcut technique that allowed them to evaluate things quicker. Okay. Nowadays, we're not going to use it that often because we do have other tools that can allow us to get that evaluation at the same time. Okay. But what we're saying here is that P of -2 equals 5, which does that generate an ordered pair that might be, or that is on that curve then? Does that make sense? Okay. So where is this leading us to? Okay. We're going to get to this here. Okay. Actually, I want to skip this. I want to go down to the factor theorem. And there's just another example there. On the sake of time, we'll skip for now. So the factor theorem. Okay, this is, the phrase here is if and only if. Does anybody remember what if and only if means to us? True. So it's like an if-then statement. And in regards to, I can only say that, x minus c is a factor if I can come up with a true argument that c is a 0 of p. As long as I know that this is, I can only get to this conclusion if that is happening in front of me, right? Basically. But the if and only if actually allows us to flip that. Basically says if c is a 0, then x minus c is a factor. But because it says if and only if, then it means I can read it right to left as well. It says if x minus c is a factor, then c is a 0. Does that kind of make sense? So that phrase if and only if really tells us that we have two conditions and 2 results that we can get from this. Okay. Essentially, the statement is reversible. It's a biconditional. That's nice because now it says if c is a 0 of p, if and only if x minus c is a factor of p of x. Well, think about what we just determined and we talked about when we evaluate. if I take P of X is equal to some polynomial, and I evaluate with some C value back, and it evaluates to give me 0, what does it tell me that C was? If the Y value that I get back is 0, if the output is 0, C must have been a what? X-intercept. Does that make sense? Okay. So this is going to allow us ultimately to take any polynomial and find the x-intercepts of any polynomial if we can determine that this evaluated y value becomes 0. But that evaluated y value, based off of this theorem right here, is the remainder, right? So if we can determine that the remainder is 0, that tells us the thing that we divided by must have been an x-intercept. Does that make sense? Okay. So let's get an example here. Okay. Ultimately, what's going to happen in about 3 days is we're going to say, take x cubed minus 7x plus 6 and factor it. Okay. But you need a starting point, and we haven't talked about what that starting point is and how we know what to try to factor it. Because there's an infinite number of values that we could see as being that C term, right? Okay. Right now, in order to get us an understanding of what we're doing, what we're supposed to be doing, the author will tell us one value to choose. They'll get the ball rolling for us. Okay. So here it says show that P of 1 equals 0 and use this fact to factor P of X completely. So if I use synthetic division, I'm going to use a 1. And then 0, I need my placeholder, and then -7, and then 6, right? And out here, 1 is the number that's going to go there. Okay, that's the C value, right? So synthetic division says bring my 1 down, multiply, add, multiply, gives me -6, multiply, gives you -6. So that is 0, right? Okay, remember that's your remainder. And if the remainder is 0, what that tells us, remember that's the same thing as evaluating this value of this function here at 1. You just got a result of 0. So that means when x was 1, the y value is 0. Does that make sense? So x minus 1 is a factor. Okay. Remember we said if C is a 0, C equaling 1 is a 0, then x minus C, in this case x minus 1, is a factor. Does that make sense? Okay. Well, if that's a factor, let's call that, that would have been my divisor, right? That's the thing that we divided by, d of x. What is this? What is the variable and exponent that goes to this? X squared, right? This would be x to the first, correct? So we have x squared plus x minus 6. That's our quotient, correct? Well, we got the divisor times the quotient plus the remainder, but the remainder is 0, right? Haven't we talked that that is the same thing as P of x? Okay, so this here is now a factored form of that there. Does that make sense, everybody? Now, does that red portion, does that factor further? To what? X plus 3, x minus 2. And did we now fully factor a cubic, which we previously had no ability to do? Does that make sense? Okay. Now, they had to tell us that 1. They had to give us a hint that that would divide this polynomial. Okay, it's original P of x. In the next couple days, we will work through the proof of how they knew 1 was a choice. Okay, and then once we learn that, we will then, you'll see how that can be kind of time-consuming and exhaustive. We'll use technology to kind of cheat a little bit. Yes, Sam. But those would not end up being zeros. Yes, Jim. Yes. When we get these remainders of zeros and we generate these factors, then these factors are going to produce the x-intercepts. So in this one, x minus 1 is going to give me an x-intercept at 1, right? X plus 3 is going to give me an x-intercept at negative 3, and then at 2. Does that answer your question? Yes, yes, yes. Correct. So what we find out, yes. So what we find, but what we have to do is we have to bring in the complex plane. We have to use I. But what we find out is that we have a theorem that says on the real numbers, if we're only using the real numbers, the real x-axis and the y-axis, all polynomials can be broken down to a product of linear factors and quadratic factors. Okay. Now, if we bring in the complex plane, because not all quadratics will cross the x-axis, right? Some of them are concave up in the first and second quadrant, and they don't cross the x-axis. So this quadratic here, x squared plus x minus 6, might not always be factorable on the real numbers. So then we have to bring in I. Okay, we have to bring in our imaginary numbers. But once we do that, we talk about the complex, and we'll get there. We'll talk about this later on. But once we introduce a complex plane, basically we have a theorem that says every single polynomial then can be broken down to a product of all linear factors as long as we use the complex plane. So if this would have been like x squared plus 1, that's not factorable in the real numbers, right? Because it turns into x plus I and x minus I. But I could then factor this whole thing as x minus 1 times x plus I times x minus I. So it'll probably be the first week after Thanksgiving that we start talking about that. Good question, though. There's an assignment, guys, in web assignment. It's not right now. I've got it due on Friday. Okay, you can probably get a good jump start on it, but finishing it might not be until after tomorrow's class. Is that cool? All right. Does this jog your memory a little bit from stuff that you've done in the past?